Hello everybody, welcome back to part 2 of the weak acid strong base titration. So this is going to be part 2 of this video. So if you haven't watched part 1, I recommend you do that because it gives you a little bit of background and also gives you information on how I calculated parts A and B. This video I'm going to focus on parts C, D, and E and show you how to do these, and it's really pretty much the same pattern over and over again. I'm just going to highlight a couple important spots in this video. Okay, so what I did in the last video for part B, you would do that for 11 milliliters, 8 milliliters, 19 milliliters, 75 milliliters. You would follow that same pattern over and over and over again. It's really nothing different. You just keep bouncing back and forth between the BCA table and the ice table. These 2 points, C and D, are important points along the titration I want to focus on in this video, and then the last one I'm going to show you what happens when we've destroyed the buffer and kind of killed the acid. Okay. Don't forget that I'm using HA to represent the weak acid, and A minus is my conjugate base of that weak acid. So let's go ahead and take a look. Again, recapping, 0 milliliters, I had a 2.88. I was at this point. I then increased the pH to 4.15. Notice what's happening here is I'm plateauing and flattening out at this point. Okay, because remember what I've done is after adding that base, what I've done is I've created a buffer, and that buffer keeps the pH maintained until my buffer is destroyed. Okay, and that's what we're going to start to do in these next 2 calculations. All right, so let's start with part C, and I'll show you this. Okay, so part C, what we're going to do is we're going to have 25 milliliters of the base are being added. Again, what are those major species? And again, you're going to see a lot of patterns repeating between this one and the last video. I have that weak acid, I have the sodium ion, and I have the hydroxide ion. Now what's different about this is that I'm not going to continue with where I left off last time. I'm going to start over as if 25 milliliters were added all at once. Not that we did it drip by drip or little bursts like you guys actually do titrations. We're going to mathematically calculate this as if it went from 0 to 25 immediately. All right, again, analyze what I have in here. What I have is that weak acid. I have the sodium ion, which we know doesn't do anything. Then over here I have that strong base, water, and again, these two hopefully are going to react just like we saw in the last one. Since I have a strong base, sodium hydroxide, I'm going to go ahead and write the reaction just like I did before. So HA. Okay, at this point what I have here is I have the 0.005 molar HA. That's going to stay the same because I'm always going back to square one, starting this over at the beginning. At this point I've added 0.0025 moles of the hydroxide. This is still going to go to 0, and this is still going to be left over. This is still going to be my excess. This is going to be my limiting reactant. But it's going to have something strange happen here. I guess not necessarily strange, but what we have is that number of moles just got cut in half, and it's going to be equivalent to this number of moles right here. Okay, because half of this goes away, 0.0025 is my limiting reactant. I use that to figure out how much of the conjugate base is left over. Notice that these two numbers are going to be exactly the same. This is referred, when you see this happen, this is called the halfway point. And this is really important when we deal with titrations to recognize this point because something important is going to happen here. Okay, so halfway point is being reached at this point. How do I know that? Because at the halfway point, the moles of the acid, let's do it this way, the moles of the HA equal the moles of the anion, the conjugate base. That's true when we get to the halfway point. Alright, so if I come back and I use my Henderson-Hasselbalch equation, which is that pKa plus the log of the base over the acid. Remember, you could use the ice table if you wanted at this point. It's fine, but because that pattern always emerges, the Henderson-Hasselbalch equation is way more important at this point. It's a lot faster. So 4.75 plus the log of the base, which is equal to 0.0025 moles over 0.0025 moles. Well, if I have the log of 1, that basically comes out to 0. Log of 1 is 0, so therefore this portion always drops out. So what we find is that since this part over here always drops out when we are at the halfway point, because remember at the halfway point these two moles are always equal, and if they're in the same volume, this portion will always drop out. We can say that at the halfway point my pH equals my pKa. And as a result of that, if I did and I took away the negative log on both sides, I could also say that my hydrogen concentration is equal to my Ka. This is really important to memorize this because I guess I wouldn't say memorize it, but if you understand the logic of what's happening, it's just pretty easy to get this information, because this is a way to find the Ka of an unknown acid. And this is what we're going to do in our next lab. We're going to find the unknown acid's Ka by finding the halfway point. So it's really important and critical to remember that. So I come here, this is half equivalency. I like to call it the halfway point. A lot of textbooks and a lot of chemists do. So at this point here, we've reached 25 milliliters. So at 25 milliliters, my pH still is not that much. I'm going to kind of bring this number over here, is 4.75. So it still has reached, it's still maintaining that pH of about 4.75. Now the thing about this though is, take a look at this. My pKa is 4.75. My buffer maintains the pH around that region. So for this particular acid, this acidic acid, it will always maintain a pH of around 4.75. So we can use the pKa to quickly figure out if I wanted to maintain the this buffer at 5.75, I wouldn't use this one. I'd find another acid that has a pKa of about 5.75, something along those lines. So every acid has its own unique Ka, which we can then use to find a way to buffer the solution to whatever we want. Okay, and I'll talk a little bit more about that at the end. So here, 4.75. Okay, all right, so let's continue on. Okay, now I'm going to do part D, which is the 50 milliliters of the sodium hydroxide reached. I'm going to just go through everything. I think you get the idea with the major species. I'm going to go ahead and set this all up, and then we'll talk about it. Okay, so I set up the BCA table using the strong acid again. Remember, strong acid, BCA table goes to completion. I figured out the moles using molarity times volume. This doesn't do anything. It's a strong base reacting with the weak acid, blah, blah, blah. You've seen this over and over and over again. This is what happens in a titration, guys. You're always going to do a BCA table followed up with a Henderson-Hasselbalch or an ice table. Okay. Now, here's a very important part to notice. We've got these two go to 0. This is known as your neutral, I would say neutralization, but I'm going to go back and call this the equivalence point. Okay, because at the equivalence point, then we have the moles of the acid. Typically, if this is just a monoprotic acid, by the way, this isn't for polyprotic, or if you have a hydroxide with 2 hydrogens or hydroxides in there, isn't always completely true, but what happens is this is equal to the hydroxide. That's what we mean at the equivalence point. You've reached the point at which the base has become equivalent to the acid. Okay. Now at this point, what are the major species that we have left over? Okay, that's kind of the important part to look at. So let's see what we have left over here. Well, do I have any of the acid? No, that's all gone. Yeah, I still have that sodium ion. We'll kind of put that here if you want. Hydroxide is gone, so that's gone. That's gone. The water is still there, but notice there's something else now left over. Oops, there's something else that's been put into solution. I now have my conjugate base. So that's what's going to happen. Now what I have is a conjugate base that's left over that's going to react with the water. This is referred to as the hydrolysis of salts. Okay, so this is my hydrolysis of a salt. And the salt that I'm going to be hydrolysizing would be the sodium acetate, because remember, this is acidic acid, or the acetate anion, so it's NaC2H3O2 in this salt. So I'm not really focusing on the sodium, it's more that anion that's left over, because that's going to do the reaction with water. So I'll set that up and show you that. Okay, so I've got the basic framework set up. I'm taking that conjugate base and reacting with the water. Go back if you need to and watch the videos on hydrolysis of the salts. Everything we're doing in these titrations is nothing new. It's just taking all the pieces we've been doing since the equilibrium started and putting it all together into one big thing called the titration curves. Alright, so I'm going to take the hydrolysis of the salt reaction, put this in. Now I need a concentration here. Now I cannot use the Henderson-Hasselbalch equation because I no longer have the buffer. The buffer has been destroyed, so I cannot use the Henderson-Hasselbalch is only for buffers. So what I need to do is I need to figure out what concentration I have of the anion, and that's going to be taking that 0.005 moles over my total volume. Well, I had 50 milliliters, I added 50, so I have 100 milliliters, which would be 0.100 liter, so I end up having 0.05 molar solution here. And now I plug into my Kb, because now I have the conjugate base hydroxide, I should be writing a Kb. So what that means is I'm going to have to use Kw equals Ka times Kb to find the constant, or the value of Kb. Alright, so I'm plug in Ka here, plug in Kw, and solve for Kb. I'm just going to show you what Kb is. If you need to see that, go back and watch the hydrolysis of the salts reaction to get that information. So this is 5.68 times 10 to the minus 10. That's going to be my Kb value. Alright, so I'm going to plug in. Okay, at this point, I set up the Kb expression. I plugged everything in. I'm going to solve for x. Don't forget that x is equal to the hydroxide concentration, not the hydrogen concentration. I get a lot of students that get this backwards. So at this point, we got to remember the hydroxide is the value we're solving for. All right, when you solve for x, and I end up with a pH of 8.73. Don't forget to show the steps here. I know I'm not showing the steps. I'm trying to save you a little bit of time so you're not watching me do every little step. But do pH equals negative log of the concentration. Show the subtraction from 14 to get to the 8.73. But that is my pH at equivalence. Notice it is not 7. A lot of people think that when you get to the equivalence point, your pH should be 7. But it doesn't come out to that point. It comes out to be 8.73. So when I get to this equivalence, 8.73, not 7. And that's when I hit that 50 milliliter mark. So that's when I hit 50 milliliters right here. At that point, I've had the equivalence point. My moles of acid are equal to the moles of the OH minus. Okay, the moles of those two are equal, or however much acid you have is equivalent to the base. That's what they mean by equivalence point. Alright, so at this point the buffer is destroyed and all I have is that hydrolysis of a salt. So the last point I'm going to show you real quick is the 60 milliliter mark. This is really fast, so let me set that all up for you. Okay, so if you do this last setup with the 60 milliliters, what happens is the limiting reactant has now switched. Your limiting reactant is no longer the hydroxide, it is now dominating and has pretty much killed that acid, and that's why the buffer is gone, because the buffer is no longer present because the weak acid is gone, and all you're left with is a strong base and a conjugate base of a weak acid. This is a weak base. It has no effect. This dominates everything at this point because you have your hydroxide. What are the species that are left over afterwards? Well, after I do this part, this is gone. This has no effect. This is water, and I have A minus. So I have a strong base, and I have a weak base. So what's going to dominate is going to be your strong base. That's going to have the effect. So all I need to do now is figure out the concentration of my hydroxide ion, and I'm done. I mean, well, I'll plug in a pH and all that kind of stuff, and I can get the answer. Okay, so you can see that when I finish this, what I end up with is the pH of 11.96 because my hydroxide concentration is dominating everything. Don't forget about the volume total. This should be volume total at the bottom. Don't put 50 here, but add the 50 to the 60 and then divide it by 1,000 to make it, liters. And then you should have a pH of 11.96. So let me throw that in here and it will kind of finish up the chart. So 11.96 is what I have here, and that would just be 10 milliliters after I get to this. So you can see a pH drastically goes up at that point, and that would be the 60 milliliter mark. Okay, so in the next video what I'll do is I'll talk about this curve and kind of show you some highlights of this and just kind of give you a little recap of titration curves. But that would be the calculations. Thanks.